Hey guys, welcome to your lab for electron diffraction. So this lab is very similar to Bragg diffraction in that we are going to be sending a beam into a sample, in this case graphite, and then we're going to use the diffraction of that beam in order to find out what the lattice constant of our particular crystal structure is. Okay, the only difference now is instead of using a beam of light, in the case of Bragg diffraction, it was microwaves. Now we're going to be sending a beam of electrons. And so this is going to be proof that electrons, similar to light, behave like both a particle and a wave. Okay, so let's first go over the setup here. So we have our electron gun over here, which is going to be shooting electrons into our sample, which is located some distance away from the gun. Okay, those electrons are then going to be diffracted at an angle, at symmetric angle, about this central axis here. Okay, and that angle we're going to call phi. So you can think of this as being like a cone of electrons that's coming and striking this screen here. Okay, and now if we look at this screen, what we'll see is because these electrons get diffracted symmetrically about this axis, we'll see on our screen, first of all, we'll see a central dot, which is all of the electrons that did not get diffracted. Those are the electrons that just continue to pass through the crystal without being diffracted, so you'll see a bright central dot. And then we'll see various rings that correspond to these different diffraction angles. All right, and these rings are where the two outgoing waves have been diffracted and are combining constructively. So all of this should sound very familiar to you. Okay, so we'll get a diffraction ring, an inner diffraction ring that corresponds to the first order diffraction for the 1, 0, 0 plane. And then we'll also get another outer ring that corresponds to the first order diffraction for the 1, 1, 0 plane. Okay, and then from the diameter of these rings and from the power and from the voltage that we're supplying to accelerate these electrons, we'll be able to determine the lattice constant A for our particular setup, or for our particular sample here. Okay, but to get to that point, we have to go through quite a bit of theory in order to get from measuring diameters to measuring the atomic lattice spacing of our graphite crystal. The first thing that we need to do is kind of zoom in on what's happening here, where these are being diffracted. Okay, and that's what we have drawn here. And so this is going to look very similar, and actually exactly the same as what we saw for Bragg diffraction, right, where we have our incoming beams striking our sample, and then they'll get reflected or diffracted at an angle equal to the incident angle. Okay, and so these are going to be diffracted at an angle incident to whatever plane that we're looking at, and that angle we call theta. Right, so again, this should all look very familiar. And now if these two outgoing waves are going to interact constructively, which is where we see these bright rings here, right, we have this equation, Bragg's condition, that relates the wavelength of these waves to the interplanar spacing, d, and the angle at which they are reflected. So we have 2d sine theta. Okay, and what we need to do now is relate this angle theta to this angle phi. Okay, so this angle phi we can calculate because this distance we can measure, which is going to be half the diameter, right? This full thing would be the diameter of one of these concentric circles. So this little part here is half the diameter, and then the length from our viewing screen to our sample we're going to call L. So we can say that the sine of phi is equal to d2 over L. All right, now we're going to do what's called a small angle approximation. So we're going to, instead of writing sine of phi, if phi is very small, we can just approximate it as just phi, and that's going to be equal to d over 2 over L. Okay, and so phi is the angle between the particles that just pass straight through our sample without getting diffracted and the reflected beam, right? So if we then compare that to this picture down here, right, if these are coming through and going straight through, this line right here of these incoming beams of electrons that just pass straight through the sample is the same as this line going across here, right? So the angle between this line of the electrons that just passes through and our reflected beam, which is there, that's going to be our phi. So this is theta, and then that's phi. So this phi that I've drawn here is the same as this angle phi here. And you can see from this picture that phi is going to be equal to 2 theta. Okay, so let's just do some algebra now. So we can then, from this equation here and this equation here, we can then rewrite these as 2 theta is equal to d over 2 over L. All right. From this equation here, Bragg's condition, we can say that n lambda is equal to 2d theta, because again, we're using that small angle approximation. So the sine of theta is approximately just equal to theta if we're talking about very small angles, which we will be in this lab. Okay. So from this equation, you can see that 2 theta is equal to n lambda over d. And so if we just plug that into there, we will get 2, we will get n lambda over d. And this d is dhkl, sorry, the interatomic spacing. So we just forgot our little subscript on this, dhkl. Okay, and that's going to be equal to capital D over 2L. And if we just do a little bit more rearrangement, we are left with n lambda is equal to our interatomic spacing, dhkl, times the diameter over 2 times the length L. Okay, so that was just a lot of algebra to get to this equation here. And so from this equation, we are going to be able to determine the lattice constant, because if you remember, dhkl can be written in terms of a lattice constant times these Miller indices hkl. So for a cubic structure, dhkl is going to be equal to a over the square root of h squared plus k squared plus L squared. And we can rewrite this, we can simplify this further. We will just say that it's a times what we'll call FHKL, where FHKL is just equal to 1 over the square root of h squared plus k squared plus L squared. Okay, so this is for the cubic case. The problem is, in this lab, we don't know what the structure of our particular sample is. We just know that it's graphite. So unless we look it up, which we're not going to do, right? Unless we look it up, we don't know what this structure is. So we have to look at also some other types of crystal structures. The other one that we're going to look at is going to be the hexagonal. So we're going to try to determine, is this is the structure of this graphite, is it a cubic structure or is it hexagonal? Okay, and it turns out the equation for dhkl, the interatomic spacing or interplanar spacing for a hexagonal structure, is given by the following equation: a over the square root of 4/3 h squared plus k hk plus k squared if L is equal to 0. Okay, so because we're looking at planes that have L is always 0, so this is 0 and this is 0, right? And the HKL, L is always 0. If that's true, if L is equal to 0, we can write our DHKL in this form for hexagonal. Okay, and we can simplify this into A, F, HK, HKL, where F, HKL for the hexagonal structure is going to be equal to 1 over this denominator here. So we'll go ahead and rewrite it, I guess. H squared plus HK plus K squared. Okay, so let's go ahead and rewrite this equation now. But instead of DHKL, we're going to write it in terms of FHKL. So this is going to be A. What we're looking for, again, is this lattice constant A, right, times FHKL times D over 2L. All right. So what we need to figure out, are we a cubic lattice or are we a hexagonal lattice? And that'll let us know which of these two values of HKL we need to use in this equation. So we will come back to that later. But right now, what we also need to focus on is this lambda. Okay, because you may have already thought about this, but what is the wavelength of a beam of electrons, right? How does an electron have a wavelength? And so that's where de Broglie comes in. So we have de Broglie's equation, and he figured out that the wavelength of any particle can be written in terms as a Planck's constant over the momentum p. Okay, or if we want to rewrite p, we can say h over mv. All right, so we can rewrite the momentum, or we can rewrite the wavelength of our electrons in that equation. In this equation, let's go ahead and rewrite it so we don't forget what that was. And lambda was equal to A F H K L D over 2L. So instead of lambda here, we can write h over the momentum. But we also need to find out, okay, now what's our expression for the momentum of these electrons? And to do that, we're going to utilize the conservation of energy. So we know that the energy that these electrons have as they leave the gun is going to be kinetic energy. And that has to be equal to the electrical energy supplied by the accelerating voltage, which is just the charge of an electron times the voltage. That's the equation for electrical energy, is just charge times voltage. Okay, so from this now, we can see that mv squared is going to be equal to 2 times E times the voltage. We can multiply both sides by m, so we have mv quantity squared now is going to be equal to 2m charge of an electron times the voltage. And finally, we can get an expression for the momentum in terms of our accelerating voltage, and it's going to be equal to the square root of 2 times the mass of the electron times the charge of the electron times the voltage that we're supplying. All right, now let's go ahead and plug this now back into here. So we're just, again, doing a lot of algebra, trying to get to the point where we can use these equations. And each equation has quantities that we can actually measure. So our lambda now, instead of h over mv, we have h over the square root of 2m ev. Okay, so that is our expression for the wavelength. So now we can go back and plug this equation back into this first one that we talked about. And so our final equation, and the one that we're going to talk about now, is this. FHKL D over 2L. Okay, so this is the main equation that we wanted to arrive at and that we now can analyze. All right, so you can see that what I want to find is A, Okay, I can control the velocity or the energy of the electrons by changing V, and in doing so, I'm going to be changing the diameter of those concentric rings. Okay, so coming back here, looking at our picture, if I change the amount of voltage that I'm supplying to this electron gun, it's going to change the diameter of these rings. Okay, and from that, I can graph the diameter versus the voltage, and then from the slope, I'll be able to determine this value A. But we still don't know what this FHKL value is. So we're going to have two unknowns. We don't know what A is, we don't know what the lattice spacing A is, and we don't know what this factor FHKL is. So we first have to find out what is FHKL. And to do that, we're going to make two graphs. So we're going to have two graphs. We're going to graph them on two lines on the same graph. And on the Y, we're going to graph our diameter over distance L, the diameter of those concentric rings over the distance L. Oh, and then on the X, we're going to graph 1 over the square root of the voltage. So let's go ahead and put this boxed equation into a linear form so we can figure out what the slope of these lines is going to be. So if we do some algebra, and we get d over L by itself on one side, which is our Y variable, we'll be left with 2 over A F H K L square root of 2m E times 1 over the square root of voltage, which is our X. So this is our X, this is our Y, and all of this stuff will be our slope, which again has two unknowns. It has the lattice constant A, and it has this FHKL value, which we don't know. Okay, so when we graph our two lines, one for the inner diameter, so we'll measure the inner diameter and we'll graph it versus the different voltages. So we'll have one line corresponding to the inner, so this would be inner, which again is the 1, 0, 0 plane. So those are the electrons that have diffracted off of this plane. And then we'll have an outer ring, which corresponds to the electrons that were diffracted off of the 1, 1, 0 plane. Now, the slope of this inner line, right, is going to be equal to 2 over a F100 square root of 2m E. And the slope of this outer line is going to be equal to 2 over a F110, right, because this is now the 110 plane that we're looking at, square root of 2m E. All right. So if I look at this now and I take the ratio of these two values, this 2 and this A and this 2 MME, all of that is the same for both the inner and the outer. The only difference is these HKL values. Okay, so we can find, by taking the ratio of these slopes, we can find the ratio of these two FHKL values. So if we do that, outer slope divided by the inner slope, you'll end up getting F00 over F110, right? And it turns out that this value is going to be unique depending on the type of cubic lattice that we're talking about, or the type of lattice that we're talking about. So for a cubic lattice, right, this ratio of F100 over F110 is going to be equal to 1 for F100. And you can just go back using these equations that we found down here for these FHKL values, and you can plug in 100 and 110, and you can confirm this, and you should confirm this, right? And then we divide that by the F110 for that cubic one, and that's going to be 1 over the square root of 2. So if we get if our lattice is cubic, we'll get a ratio of these two values to be the square root of 2. So if the ratio of our two slopes is equal to the square root of 2, we will then have a cubic lattice, and that'll tell us then which values to use for these two FHKL values. Okay. Now if we have hexagonal, right, our F100 divided by F110. We're now using this equation, coming back here. We're now using this equation for the hexagonal HKL values. And if we do that, you'll find that the F100 is going to be equal to the square root of 3 over 2. And you'll find that the F110 value is going to be equal to 1/2, which means this ratio is the square root of 3. Okay, so if our two slopes have a diameter or have a ratio of the square root of 3, then we'll use these two FHKL values here versus these here. Okay, and so that's how we're going to find which values we need to multiply our inner and our outer diameter by. If it turns out that we have a cubic lattice, you'll take the inner diameter and you'll multiply it by 1, and you'll take the outer and you'll multiply it by 1 over the square root of 2. If we have a hexagonal, right, so if our slope has a ratio of square root of 3, then we need to take these inner values and multiply by the square root of 3 over 2, and we'll take the outer and we'll multiply by 1/2. Okay, and in doing so, we can create another graph, but this graph will only have one line, where on our y-axis, instead of graphing d over L, we're now graphing FHKL times d over L, where we take the corresponding FHKL values and multiply it by the corresponding diameter. So make sure that for the inner, you're using the FHKL for 100, and for the outer data, you multiply it by the FHKL for the 110. Okay? And then for our x, we're still going to have 1 over the square root of v. And so we're going to have some graph here. And then looking back at our equation here, but we've now moved this FHKL value and multiplied it over here. So what we're left with in our slope is just going to be 2 over a square root of 2me. All right, and then this is how we're going to find our lattice constant A for whichever one that we're talking about, for whichever lattice that we're talking about. So this lattice constant A for a cubic, remember, so if our structure is cubic, lattice constant A is just this distance here. It's actually just the nearest neighbor distance. So that's what A is defined as, is these two vectors, or those two distances. If we have a hexagonal structure, it turns out that the lattice constant A is actually these distances. So if we have our atoms arranged in a hexagon, the A is actually not the nearest neighbor distance. The A is from this point to that point, or that point to that point, right? So that's what, so if this is hexagonal, this is the distance that you're finding. The lattice constant A, that's the distance that you're finding, and if it ends up being cubic, you're just finding the nearest neighbor distance. Okay, and that is the lab. So I know there's a lot of analysis, a lot of algebra to get to this point here. But the takeaway is that just by measuring the diameter of these concentric rings, we can determine, by measuring diameter at varying voltages, right, we can then find what this lattice constant and what the interplanar spacing is for our crystal structure. And we can also, not only that, we can determine what the shape of the crystal structure is by looking at the ratios of these FHKA values. So not only are you finding the lattice constant A, but you're actually determining what is the structure, what does the crystal look like at an atomic level. Okay, so what you'll see next is I'll just demonstrate how you go about measuring these diameters and changing the voltages. It's actually pretty straightforward for this lab, so while there is a lot of analysis, the actual obtaining of data is not very difficult for this lab. Okay guys, we'll see you in a second. Okay guys, here's the two setups, or the two instruments that we're going to be using for the electron diffraction lab. So the reason that we use two different setups is if you look at the amount of voltage that each can supply, so this one can only go from 0 to 5 kilovolts, whereas this one we can go from 0 to 10 kilovolts. So we're using two different instruments because one we're able to reach higher voltages with. So before we look at the high voltage one, we're going to first look at this setup here, okay? And so what we're going to do is we're going to go ahead and turn our voltage up. I believe the first data point is around 2.5 kilovolts. And we'll demonstrate how you would go about finding the diameters. Okay, so we have that set up at 2.5 kilovolts, and hopefully you can see it. Yeah, you can kind of see it. It's easier, it's more readily apparent in person, but you can see an inner ring here that we would measure the diameter of, and an outer ring there. Okay, and then all we would need to do now is go to our next data point, whatever it happens to be. Let's just go to 3 kilovolts. And we would again measure the inner diameter and this outer diameter. And so, yeah, taking data for this lab is pretty straightforward. You just change your voltage, measure your diameters, change the voltage, measure your two new diameters. Okay. So we've maxed this guy out. So once we've gotten all the way to 5 volts or 5 kilovolts, we're gonna then come over here. So this one I already have set up for 6 kilovolts. Let's see if we can get it to zoom in on what's happening on this screen. So yeah, you can kind of see it, and you can see that there's an inner ring. Let's see if it'll focus. Okay, so hopefully you can see that there's an inner ring here, and then there's an outer ring there that we would measure the two diameters for. Now this one's a little bit different in that whenever we change our voltage, so let's go to 7 kilovolts. Right, when we change the voltage, you'll see that my pattern has disappeared. And so that's why we can move the beam. So we can move the beam using this vertical and horizontal adjustments. And in doing so, we can hopefully recapture that pattern. There we go. Okay. And so, again, it's hard to see on the phone. It doesn't like to pick it up. But hopefully you can kind of see those concentric rings. It's much easier to see in person. But there's this central ring here, okay? And then there's another outer ring. And then we get these higher order rings way out here that are just different diffraction orders of those two inner rings, okay? So we only want to look at the two inner ones. But we would measure the diameter in the same way. So you just change the voltage, measure the diameter, change the voltage, move the beam around until you can again see the pattern, measure the diameters, okay? So again, pretty straightforward for this lab, but that's how you would go ahead, that's how you would collect the data of the diameters at varying voltages. And then from that, you can determine not only the lattice spacing, but the type of lattice structure for our graphite crystal. Okay, so that's going to be it for this lab, and we will see you next time, guys.